Hello, my name is Piotr, and today I'll talk about Scylla Rust driver, our motivation for implementing it, important design decisions, and our future plans. I work on Scylla core by day, but lately I also started leading and maintaining the Scylla Rust driver effort. The idea to implement a new SQL Rust driver from scratch emerged during an internal hackathon at ScyllaDB around 2 years ago. The Rust ecosystem already had a few drivers available, but none of them really fit our needs for a multitude of reasons. Unsatisfying performance, node bugs, and so on. One of the options was CDRS, which now looks discontinued and forked as CDRS Tokio, which is coded in pure Rust, but it had a bunch of performance issues, wasn't asynchronous, and had a few known bugs. The other option was Cassandra CPP, which is based on the C++ driver. The project simply provides a thin Rust interface and binds it to the C++ core. Thus we decided to use our experience with existing drivers and carefully plan a new open source Rust driver written natively in Rust and with very specific goals in mind. First of all, you want it to be asynchronous from day one. Then it should support token awareness and shard awareness. And it should be fast, produce as little overhead as possible, and be easy to extend. And based on these ideals, we started coding Scylla Rust driver. A short interlude. Asynchronous Rust is based on a rather unique approach, namely a future promise model in which a future represents the computation itself, not just a result of a task that gets executed in the background, which is common for other languages that support asynchronous operations. In async Rust, nothing is implicitly started in the background, and instead it's the programmer's responsibility to advance the state of asynchronous computations. And in order to do that, a runtime is customarily used. A runtime includes the capabilities of a scheduler, the event loop, the reactor, and so on. Due to async Rust design, runtime is not part of the language, but instead there are multiple runtimes to choose from, most of them open source. And we picked Tokio. Tokio is pretty much a standard choice due to its very active development community, lots of features, and general ease of use, and of course popularity. Side note, it would be perfect, we would like it very much, to write our driver in a runtime agnostic way, but we decided that the ecosystem is not yet ready for it. There are tons of important bits in Tokio, like good TCP utils, timers, and other things that are not easy to code in a generic way. And now let's go back to our driver. We want the interface to be straightforward yet powerful. Many of the details can be configured, but we also provide default values for everything that makes sense for us. For instance, when a user wants to establish a SQL session with Scylla, the only required parameter is the address of one of the nodes. And a session is pretty much everything that the user needs to create to start communicating with the database. With the help of a session, it's possible to simply send requests and receive the results from the database. Depending on the workload type, users might want to specify a custom number of connections to the database nodes. Our default establishes a single connection per shard per each node, but users are free to define a fixed number of connections if it fits better to their workloads. And by the way, per shard connections are a Scylla-specific feature, but Cassandra users can also benefit from our driver in full. It is fully compatible with Cassandra as well. For Cassandra, we simply create one connection per node by default. Token-aware routing, supported in our driver from the start, is a load balancing policy which computes token values from queries on the client side and tries to send the requests straight to the database nodes which own the particular data. This strategy is pretty much a must-have for workloads which care about low latency. It's important to remember that token awareness works correctly only when prepared statements are used. And that's not usually an issue because prepared statements are a huge performance boost anyway. So most applications are already coded with prepared statements in mind. Our driver here is of course no exception. We fully support preparing statements, executing them later, and making sure that everything is automatically re-prepared when needed. And our driver also takes it one step further. Once a request is ready to be sent, the driver will try to send it not only to the node that has the data, but directly to the CPU core, which owns a particular partition. That translates to even better latency because the data goes straight to the shard responsible for handling the request. And that's possible because by default, Scylla driver maintains a separate connection for each core and keeps up-to-date topology information cached on the client side, which says which data belongs to which CPU in which node. Next thing that we're quite proud of are observability tools available for Scylla driver users. Firstly, the driver is integrated with a tracing crate, which provides a way of integrating multiple login environments, be it printing the logs to your screen, saving them on disk for later, sending them to an external observability tool or service, anything you imagine. That's very useful for debugging and looking for bottlenecks, but also for more complex analysis, gathering statistics, etc. Our driver also exposes a number of useful metrics on its own. For instance, how many requests were sent in each session, what was their latency, how many of them were successful, how many of them returned errors, and many more. We're also integrated with the CQL tracing mechanism. In CQL, each query can be individually traced so that a detailed list of steps and their timestamps can be later investigated, for instance, in search for performance regressions. Our driver fully supports query tracing, and its results can be simply printed to logs or saved for later more complex analysis. You can see in the slide that it's possible to deduce which step took how many microseconds, how many nodes were contacted, how long it took for the database to actually fetch the data from disk, was the data already in cache, did we need to touch the disk at all, and so on. All in all, tracing output is full of very important details which are invaluable for diagnosing potential performance issues. Load balancing policy is a very important aspect of a CQL driver. A load balancing policy fitting to the workload can ensure satisfying the latency and availability requirements. And our driver's default policy is called token-aware round-robin, which means that we'll first prepare a list of nodes responsible for a particular partition, and then pick one of the nodes in a round-robin fashion from this list. On top of that, we'll also try to reach the appropriate shard directly. Aside from the default policy, users are able to pick something else. For instance, DC-aware round-robin, which is useful in multi-data center scenarios to make sure that we prefer contacting nodes from the same data center. Finally, users can implement their own custom load balancing policy if they believe it will better suit their needs. Such a custom policy can be implemented in Rust by using a trait that we prepared for that purpose and showed on this slide. Retry policy is also very important for latency as well as availability. While not useful at all when the connection behaves correctly, retry policy is used when a query fails for some reason. By default, our driver will retry such a query, but only if two conditions are met. First of all, the error type must suggest that a retry makes sense. For instance, a timeout might make sense because the next time we try, maybe the node will keep up with us and return the results. If the error sounds permanent, for instance, it's invalid query syntax, such a query will not be retried because it makes no sense. And the second condition is that the driver must be able to deduce if the query can be retried without any side effects. In other words, if it's idempotent. A user can explicitly mark a query as idempotent to let the driver know that it's safe to retry. And same as with load balancing policies, users can implement their own retry policies if the available ones are not good enough for some specific workloads. That can be done by implementing two traits that we provide and that you can see on this slide. We also take the performance of Scylla-RAS driver very seriously. As part of the effort, we continuously run benchmarks against other drivers to make sure that we remain competitive. On the next few slides, I'll present a few results from a recent run. Our benchmarks are open sourced, just like the rest of the code, so you're welcome to rerun the experiments yourself. You can find the links on this slide. And in this particular experiment, we compared Scylla-RAS driver against Scylla C++ driver, which is our shardware implementation of the C++ driver, DataStax C++ driver, which is implemented with Cassandra in mind, so not shardware. Then Cassandra CPP, which is a Rust driver, which is a wrapper over DataStax's C++ driver. And finally, GoSQL, a driver implemented in Go with additional shard awareness provided by us. So this chart shows how many milliseconds it took for the tested drivers to perform 1 million inserts into a Scylla node, which has 16 CPU cores, so 16 shards, for a few different values of concurrency. Measuring different concurrency values lets us check a broader spectrum of workloads and also see if the driver scales linearly along with increasing concurrency, which is a desired trait. Here is a similar run, but this time the workload consists of 500,000 inserts and 500,000 reads intertwined with each other. And we can observe that the results are quite similar to the first workload, which only wrote to the database. And finally, a workload consisting of database selects only. A few conclusions that we are very happy to make after the tests are: first, Scylla-RAS driver is generally faster than any other driver we compared against. Second, it's very close to the performance of drivers coded in C++, which were previously de facto treated as reference implementations in terms of performance. They were simply the fastest. And then that our driver scales very well when concurrency is increased, which is very nice because usually people tend to use Scylla for scenarios which demand high scalable concurrency. Now, the sole fact that our driver is coded in Rust makes it much easier to hunt for potential bottlenecks and other performance issues. One of the tools from the Rust ecosystem that helped us a lot is Cargo Flame Graph, a wrapper over Brendan Gregg's Flame Graph toolkit integrated into Rust's build system Cargo. With Cargo Flame Graph, it's extremely easy to run your program under a profiler and generate a graph of calls, which shows which function calls took longest to execute. This is how the output looks like. It's full of details and not much can be seen on a single slide, but this generated flame graph is interactive. You can zoom in on specific parts of it to see how much time the processor spent inside certain frames. By studying flame graphs, we were already able to identify a few bottlenecks in our previous releases of our driver, including some that were caused by lack of buffering reads and writes when reading and writing to and from TCP sockets. It was clear on the flame graph output that our driver spent way too much time on syscalls related to TCP networking, send message and receive message. And all of these problems are already fixed, thanks to thanks to flame graphs, and the newest release already has very nice performance. Then, since our project is based on Tokio, as I mentioned before, since a few weeks we can also leverage another very nice tool called Tokio Console. It's a task manager that looks like the top utility in Linux that I'm used to using, but it works directly on Rust futures. With that you can browse which tasks are currently active, which resources like semaphores or queues are taken and which are free, and so on. All in all, it's a very useful tool for investigating how your async code looks underneath and how it works. We also have a big plan of replacing other drivers with bindings to our one true driver, Scylla driver. A single centralized implementation would make it easier to maintain, and Rust's superior performance can speed up the solutions available in other languages like Python, Ruby, or any other dynamic languages that tend to be slower. We actually already have a working proof of concept for replacing our C++ driver with Rust bindings. You can take a look at it under the link. And more languages are already on the roadmap, so stay tuned. Finally, I'd like to take a moment to thank our existing open source contributors from the community. We already accepted a number of fantastic contributions, and I'd like to hereby invite everyone interested to join our effort and contribute as well. Thanks to our community, we now have a special implementation of a session that automatically prepares all statements. We can customize connection timeouts, our serialization routines got faster. We no longer have certain issues with user-defined types, etc. The list is actually much longer, but I can only fit so much in a single slide. In any case, we're happy to answer any questions on GitHub and help with any issues if somebody wants to become a contributor. Finally, our driver has a very nice quick start guide and thorough documentation. And it's also officially out on the Rust package manager crates. So go ahead and give it a try. Thanks everyone. Feel free to reach out to me if you have any questions about the presentation or anything else. Thanks.